All right, everybody, welcome back to Chapter 7. We're going to just keep on going through. Today we're starting on quantum numbers. So quantum numbers are going to be electron descriptions. So where are electrons at inside of an atom? So we'll just start in with your principal quantum number. Your principal quantum number is going to be, as you see here, n. It can take any positive integer value, 1, 2, 3, 4, so on and so forth. It's going to describe, this is the energy shell that you're in. You know, when we were talking about electrons exciting, uh, when you get more advanced, electrons can still excite within a single energy shell, but at least through when we were working with the Bohr model, we were talking about electrons, say, absorbing a photon and jumping from n equals 1 to n equals 3. That's an excitation, and you can calculate the energy of that photon. Or if an electron relaxes from n equals 3 to n equals 2, it's going to release a photon, and we can calculate the wavelength of that photon, so on and so forth. This is going to also dictate the size of atomic orbitals, and you'll see that when we're talking about nodes. Your second quantum number is your angular momentum number, or L. L is going to dictate the shape of your orbitals, and it's L is your represents your subshell. And so each value of L, so L can take values of 0 up to n minus 1. So like if I have n equals 4, if I'm in the n equals 4 shell, then the L values I have that are possible are 0, 1, 2, and 3. And so you'll see that each one of these L values aligns with a subshell. So like L equals 0 is your S subshell, L equals 1 is your P subshell, so on and so forth. And so again, this is going to dictate the shape of an orbital. The next quantum number is your magnetic quantum number, M sub L. This quantum number is it gives you individual orbitals. So within a subshell, you're going to have orbitals of varying numbers based off the subshell. And so your M sub L, whatever number that is, that's one of the orbitals inside the subshell. And so your M sub L can take values of minus L to plus L. And so you can start to get an idea of how many electrons are possible based off a set of quantum numbers. And we will have a fourth one here in a little bit, but let's just work with these three for a while because now imagine that you have, well, you can start to calculate the possible number of electrons because each individual orbital can hold 2 electrons. And so every single value of M sub L can hold 2 electrons. So if you have 5 values of M sub L, which you'll see here in a couple minutes, you have 10 possible electrons. So let's just start looking at a couple of quantum numbers. So if I have L equals 0, that's my S subshell. And so my values of M sub L, the only value I can have is 0 because minus 0 to 0 is just the one value. So that means that this subshell has one orbital because there's only one value of M sub L. So this has a maximum of 2 electrons. And this is true for every S subshell, whether it's a 1s, 2s, 3s, so on and so forth. And that's where your value of n comes in. So it's like when you see electron configurations, you're going to see like 1s, 2s, 3s. This first number here is your value of n. Let's talk about the L equals 1 subshell. Well, your M sub L values are minus 1, 0, and 1. So you see I have 3 values, 1, 2, 3. That's 3 orbitals. L equals 1 is the P subshell. So every P subshell has 3 orbitals, or maximum of 6 electrons. This is we also want to bring in the idea of degeneracy. So here you see degeneracy is orbitals having the same energy. And so within the orbitals on this slide here, so in your p subshell, all three of those orbitals are degenerate. So they're at the exact same energy level. Okay, so let's look at L equals 2. The m sub L values are -2, -1, 0, 1, and 2. This is your D subshell. How many orbitals do we have here? 1, 2, 3, 4, 5. We have five orbitals in each D subshell. So if I have 5 orbitals, that's 10 possible electrons in that subshell, or each, and same for every D subshell. And again, these 5 orbitals are all degenerate. The last one we'll look at, we could go higher, but we don't really need to for our purposes, is L equals 3. The m sub L values are -3, -2, -1, 0, 1, 2, and 3, which is 1, 2, 3, 4, 5, 6, 7 orbitals. This, of course, is your F subshell. I have 7 orbitals, 2 electrons per orbital. That's 14 electrons possible. And again, all 7 of these orbitals are degenerate. So the exact same energy. So we also want to understand what happens between, especially values of n. So here, you see like your 1s, 2s, 3s. That's your value for n. And so here, that would be your 1s orbital. That's your 1s, 2s, 1s, 2s, 3s. And these look like rings, but you really want to think of them in terms of concentric spheres. So, like here, this 2s subshell is actually going to be a sphere around the 1s orbital. So, and the same for the 3s. So you have a sphere inside of a sphere inside of a sphere. Uh, so that's the way you want to think. All s orbitals are spheres, but down here at the bottom, you also see p orbitals. And notice here how you would have 2p, that small one in the middle. 3p is the next larger. Let's see. And then 4p would be bigger yet. And so what you're seeing here is what we call nodes. So between each shell, you're going to get a node or an area of 0 electron density. And so it's a quantumly forbidden zone. And so that's going to be these spaces in here. So remember we talked about the probability density? So for these spaces, your probability density is 0, yeah, or at least it goes to 0. And you can actually see the nodes on the probability density graph. So it's like for 2s, you imagine that most of your probability density is going to be in this outer sphere with a little bit in at the 1s shell, but then you see this area that touches the 0 line, that's a node. Or for the 3s, you're going to have your 1s shell, your 2s shell, your 3s shell, and then a node between each shell. And so again, that's going to be a quantum mechanically forbidden zone. You're going to get uh, a probability that goes to 0 of finding an electron in one of those regions. You can see the nodes on the p subshells as well. These void spaces. The the orbitals that we look at are maps of solutions for the various levels of the hydrogen atom. So of course we talked about we do that because the hydrogen atom has the one electron in the nucleus, and we really have a two-body problem, something we can solve. When you start getting to what's called polyelectronic atoms, so multiple electrons, the solution becomes quite a bit harder. Now, computational chemistry is still making advances on this and working on it, but uh, we're still basing these off. We still base a lot of our solutions off the solutions to the hydrogen atom. And you find that those solutions are very accurate for all atoms anyway. So they're a very good approximation. A couple of things that will start to happen, though, in a polyelectronic atom is outer electrons are going to be affected by inner electrons. So they get what's called shielding or screening. And so what that really is there's an electrostatic attraction between the positive nucleus and the negative electrons. However, electrons that are here closer to the nucleus experience the entire attraction they experience the entire nucleus, so the entire electric potential. Whereas electrons that are further out, they're experiencing attraction to the nucleus, but they're also experiencing repulsion from other electrons. And so the electrons that are further in are actually going to prevent outer electrons from experiencing the entire positive charge of the nucleus. And this is called shielding or screening. So that makes solutions for outer electrons even more difficult. So we can look at a table, we can start to put these quantum numbers together. So if you have like n equals 1, and so your L goes from 0 to n minus 1, so the only L value you can have is 0. The only n sub L value you can have is 0. So only an S subshell exists at the n equals 1 level. When you go up to n equals 2, your values of L go from 0 to n minus 1. And so your only values possible are 0 and 1. And so that means you can only have S and P subshells at the n equals 2 level. So, and then it just keeps increasing. At n equals 3, you have S, P, and D possible. Then, of course, you see your M sub L values and the number of orbitals based off the M sub L values. And so if you really want to start to get an idea of how many electrons there are in a given set of quantum numbers, first off, the more quantum numbers you have, the fewer electrons you're talking about. Now, if you're only given a value of n, you can say my maximum possible number of electrons for that value of n is 2n squared. If you're given a value of L, let's say you're given n and L, and that's all you have, your maximum number of possible electrons is 2 times 2L plus 1. So these are some quick little formulations you can use to actually figure out how many electrons are possible within a given set of quantum numbers. But think about it. So if you just have a quantum number n, let's say you have n equals 4. Well, and you look at all those possible values of L, giving you all those possible subshells. Well, that's a lot of electrons. But then if I give you the quantum numbers 4 and 2, okay, well, now I'm specifically talking about the 4D subshell. That decreases the maximum number of electrons I can have. Now, what if I gave you quantum numbers 4, 2, minus 1? And so the -1 for your M sub L. Well, now I'm only talking about a specific orbital. And so my maximum number of possible electrons is now dropped to only 2. So you see, the more quantum numbers you get, the fewer electrons you're actually talking about. And that brings us to our final quantum number, our spin quantum number. And there's only two possible values for this one, a +1/2 and a -1/2. And that has to do with, we call it upspin and downspin. It's the angular momentum energy of the electron. And it's either the angular momentum vector either goes one way or it goes the opposite way. And so if you get a set of 4 quantum numbers, you can only be talking about a single electron because, and this goes back to the Pauli exclusion principle. No two electrons in an atom can have the exact same set of quantum numbers. And that's going to be your N, L, M sub L, and M sub S. So if you have two electrons that have all those numbers the same, it's not possible. Now, you can have electrons where you have all four numbers are different. You can have electrons where uh, two numbers are different. You can have electrons where just one number is different. As long as it's not the exact same set of quantum numbers, you're fine. So we already kind of talked about this. So let's look at it a little more. For n equals 2, your values of L are possibly 0 and 1, or are 0 and 1. And that's going to be your S and P subshells with 8 electrons possible. Let's see, n equals 3, L equals 1. Now I have two quantum numbers. So now I'm at n equals 3, L equals 1 is the P subshell. So now I'm talking specifically about the 3P subshell. My values of M sub L are -1, 0, and 1, which is three possible orbitals, which means I have a maximum of six possible electrons that I'm talking about. Or I could just take that L and do 2 times 2L plus 1 and get the possible number of electrons, which will be six, corresponding to the three orbitals in the P subshell. Now, what if I have n equals 4, L equals 2, M sub L equals 1? Now I have three quantum numbers. Since I have a desert, so n equals 4, that's the fourth energy shell. L equals 2, that's going to be your D subshell. My possible orbitals are negative, my M sub L values are -2, -1, 0, 1, and 2, which gives me 5 orbitals. But I'm only talking about one of those orbitals. So M sub L equals 1, I am only talking about that orbital right there. So since I'm only talking about a single orbital, my maximum number of electrons possible are 2, because only 2 electrons can go in an orbital. And like we said, if you get 4 quantum numbers, I am specifically talking about one electron at the n equals 3 level in the S subshell, in the one orbital in the S subshell, and it has the positive one half spin. And the reason we differentiate between the angular momentum quantum number, which is here, and the spin quantum number is angular momentum has to do with the electrons actually moving and orbiting around the nucleus, whereas spin is a measure of angular momentum coming from the electron itself. So these are two different types of angular momentum. It's not electrons aren't actually little balls that are rotating, but you can think of it that way. You can put a ball on a string and swing it around, and you're getting an angular momentum from the path, the circular path the ball is taking. That's going to be akin to your value of L. But then you can take the ball and you can spin it. Well, it's still moving in a circular motion, but that circular motion is contained to the ball itself. That's where your M sub S would come in. Now, according to the Pauli exclusion principle, I cannot have another electron with those quantum numbers. However, I can have another electron that's very close. They have 3, 0, 0 for the first three quantum numbers, but this time I get a spin quantum number of a -1/2. So that's perfectly fine. You just can't have the exact same set of four quantum numbers. So let's say you were given two electrons that both had 3, 0, 0. Well, you might want to go, well, I can't have two electrons with the exact same quantum numbers. But you weren't told the fourth quantum number. So if you're not told all four quantum numbers, you don't know if you actually have that. So you have to have all four quantum numbers for the Pauli exclusion principle to apply. So let's look at an exercise. If n equals 5, what are the possible values of L? Then if L equals 3, what are the possible M sub L values? What L values are possible if an orbital has M sub L equals a -2? All right, so a couple things. I know my values of L, 0 to n minus 1. That'll help. My M sub L values are minus L to a positive L. Okay, So first I'm asked for n equals 5. What does L equal? Okay, well, if I go from 0 to n minus 1, my possible values of L are 0, 1, 2, 3, and 4. Let's look at L equals 3. What are the possible m sub L values? Well, minus L to L. And of course, that would be your F subshell. What about when m sub L is minus 2? What are your possible values of L? Can you go backwards? Well, I know that if m sub L equals minus 2, and let's say that's the extreme version, the extreme end of the m sub L. Okay, well, I know that if L equals 2, I go minus 2 to plus 2. So it exists in there. I know that for L equals 1 and L equals 0, I cannot get to m sub L equals 2. So my values of L have to be 2 and larger. All right, now we're actually getting into some electron configurations, the Aufbau principle. So the more technical definition is as protons are added to form new elements, as you add one proton, you add one electron. Now, what this is going to end up being more useful as is when you fill electrons into an electron configuration, you fill from lowest energy to highest energy. That's your Aufbau principle. Hund's rule has to do with how you fill electrons in. So let's say I have my D subshell, and I have my 5 degenerate orbitals. And then let's say that I have 5 electrons to fill into this D subshell. Okay, I have to fill them in, and I use these little half arrows. I have to fill them in like that. I can't start pairing electrons until I get above, until I get at least one electron in each one of those orbitals spinning the same direction. This is Hund's rule. So I couldn't. So let's see. What's something I couldn't have? I couldn't have that because this orbital's still empty. And that comes in for a lot of quantum mechanical reasons. So like here, and it's on a slide later, but when you have degenerate orbitals, and this D set, all these orbitals would be at the same, let's say this is the 3D subshell. They're all at the same value of n. They're all in the same subshell. One thing that stabilizes both atoms and molecules is called quantum exchange energy. And so all of these electrons, these are called indistinguishable. And so when they're all the same energy and they all spin the same way, uh, basically let's imagine your atom can, I was going to say, let's imagine your atom can think, but then that leads us into experiments that have been done that go, that would take you way down a rabbit hole if you went that way. But um, let's say your atom is actually looking at these electrons. They're all in the same subshell. They're all spinning the same direction. It can't tell one electron. It wouldn't be able to tell one electron from another. So it could put electron 5 in the place of electron 1, or electron 2 in the place of electron 5. So this is what's called exchange. And this type of delocalization is actually going to stabilize atoms. So Hund's rule is a reflection of this. So again, you cannot start filling or pairing electrons until every orbital has an electron in it. Okay. So now we're going to start talking. We're getting into electron configurations. This first periodic table here shows you your blocks. You notice you have an S block, a P block, D block, and F block. And that's going to tell you, um, and that's going to correspond to what we have up here. Now, you can use this map. A lot of students do when you're writing your electron configurations. So you see, like you would start with your 1s, and then you go to your 2s, and then 2p, 3s, 3p, 4s. After 4s, you'd get 3d, 4p, 5s. You can use this map when you're writing your configurations if you remember it, and this is what helps you. You can also tell exactly what your configuration should be based on the periodic table. Because if you look here, so when you're filling this in, your first one here is a 1s1, your second one is a 1s2, then you're going to go to row 2, and remember this is row 1, row 2, row 3, 4, 5, 6, and 7. Your S and P blocks, your value for N is going to be the row that you're, the number of the row. So here you have 2S, and you jump across and you have your 2P in the P block. And the way you're filling these in is you go 2P1, 2P2, 2P3, 2P4, 2P5, 2P6, 2S1, 2S2. So you just count across the row. And then you would go down to row 3. And for your main group elements, that's 3s and 3p. Now, when you get down to row 4, you see the 3d comes in. And these electron configurations are set up in accordance with increasing energy. So you don't just go from 4s to 4p because 3d is an energy level between the two. And so 3d is above 4s, 4p is above 3d in energy. So you want these to be in energetic order. And so then your d's, now remember, your d orbitals your d subshell has 5 orbitals, and that corresponds to your m sub l values of -2 to +2, -2, -1, 0, 1, and 2. So with 5 orbitals, you have 10 possible electrons. And if you count across the periodic table, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So you want to make sure you know your blocks. Your F block, I'm gonna show you how that works. We're really not gonna do a lot with it because I want you to get down how these main groups work. So, and your F blocks, they can get a little bit out there, but I will show you how they work. We're not going to do a ton with transition metals because we also have what's called half-fill configurations, and each individual row has its own rule. And so usually we wouldn't get into that until more advanced classes like, say, inorganic chemistry, which is a 400 level. But just know that it exists. So again, you can use this chart for your Aufbau principle, or you can just look at the periodic table, see where you're at, and know what comes next. So you'd go from 1s to 2s to 2p, 3s to 3p, 4s to 3d to 4p, 5s, 4d to 5p. Now, when we get down to row 6, that's where it's going to change a little bit. And I'll show you, you go from 6s to 4f to 5d to 6p, then 7s to 5f to 6d to 7p. And that's your energetic order. And again, you can do that up here to see how you go 4f before 5d to 6p to 7s. So again, you could go right back to your Aufbau principle chart and use that. Really, these electron configurations are going to take practice. And your value for N, let's go over that again. Your value for N for your main group elements, which is your S and P blocks, is going to be the number of the row you're in. Because you see here row 2, 2S, 2P. Now, your value for N for your D block is going to be row -1. You have row 4, but 3D. And then your F block is going to be row -2 for your value of N. You see here you have row 6. That's going to bring you down here, but you have 4F. So you have your main group elements are the row you're in. Your D block is your row -1, and your F block is your row -2. for your value for N. I think the best way to do this, though, is to just start building some electron configurations. So let's do that. Okay, so we have two types of configurations. You're going to want to know full configurations and abbreviated or noble gas configurations. Okay, so your full configurations. So let's look at this. We have lithium. Lithium is right here. Okay. So what do we have? Well, that's in row 2. I also know, based off where the atom is, what it has to end in. I know that this is my S block, and I know that that's S1 and S2. So lithium has to end, and what row are we in? Row 1, row 2. Lithium has to end in 2s1. So what do I have? I have my row 1, which I know is 1s1, 1s2, and then 2s1. Oops, hang on. And so now you've noticed the first number, that's your value of N. Then you have your subshell. And then the raised number is how many electrons you have in that subshell. And so if you're ever counting how many electrons should you have, you want to count those raised numbers. So let's look at that in another element. Okay. So the next element is nitrogen. So that's right here. Okay, so I see that's again in row 2. However, I know this time that's my P block. So what's this going to have to end in? Okay, well, this is going to have to end in 2p1, 2, 3, 2p3. So I have 1s1, 1s2 for row 1, 2s, 1 and 2, and then 2p, 1, 2, and 3. So this is going to be 1s2, 2s2, 2p3. And what I'm doing now, these are your full configurations where you start all the way back at 1s2. And you start all the way back at 1s and you just work your way through. Okay, now, how many electrons? We can look at the periodic table and say, how many electrons should nitrogen have in it? Okay, well, nitrogen's atomic number is 7. That means it has 7 protons in its nucleus. You better remember that. So for it to be neutral, it also has to have 7 electrons. Okay, well, what do I have? I have 2, 4, 5, 6, 7. So I have the proper number of electrons. All right, let's look at beryllium. Where's that at? That is going to be right here. So that has to end in 2s2. So 1s2, 2s2. And then oxygen, which is right next to nitrogen. Let's see, that's got to end in, so if nitrogen was 2p3, oxygen has to be 2p4. So 1s2, 2s2, 2p4. And again, these electron configurations are in the order of ascending energy. So energy is increasing that way. All right, let's look at some more. Okay. Before we move on, I want to demonstrate Hund's rule again for you. I'm going to draw what's called a box diagram, okay? So if you're ever asked for a box diagram, now in your textbook, they actually draw boxes. I don't do that. I draw lines. And so if you go to nitrogen, your 1s is your lowest in energy, so we draw it down here. Then you have your 2s is a different energy shell, so it's higher in energy, and then your 2p, because remember, p subshells have 3 orbitals. Go back to your quantum numbers. And it's slightly higher in energy than your 2s. So then you say, well, I have to fill in lowest energy to highest energy, and I have to fill in 7 electrons. So there's 1, 2, 3, 4. Now I have to fill in 3 electrons for my 2p. I have to fill in 1, 2, 3. That's Hund's rule. Okay, let's do the box diagram for oxygen to see the difference. 1s, 2s, 2p. Now I have to fill in 8 electrons. What the heck? No. Yeah. 1, 2, 3, 4. I still do it this way, 5, 6, 7, just to make sure you don't miss an orbital. And now that I have one more electron to fill in, I can come back and go 8. And so all the way over to your noble gas, so which would be neon, you would just keep filling in your electrons. So these are called box diagrams. In a little bit, you're going to be doing what's called a valence shell, a valence electron box diagram. But let's look at a few more of these. So magnesium, okay, that's right here. Now this is in row 1, 2, 3, and it's in the S block. So this one's going to have to end in S2. So let's do row 1, 1s2 from hydrogen to helium. Let's do row 2. Lithium and beryllium are going to get me 2s2. And then boron to neon, 1, 2, 3, 4, 5, 6. That's going to be 2p6. And then sodium and magnesium, 1, 2, 3, s2. All right, what about silicon? And remember, I started all the way back at 1s. These are full configurations. Okay, so silicon, where's it at? It's right here underneath carbon. And it's also in row 3. So what does it have to end in? You're going to go 3s1, 3s2 from sodium and magnesium, jump over to 3p, and you see you have 3p1, 3p2. So this has to end in 3p2. So that's 1s2. So row 1, we're going to go to row 2, lithium, beryllium, 2s1 and 2. Go over to boron all the way across, you get 2p6. Sodium and magnesium are going to give you 3s2. And then aluminum and silicone are going to give you 3p2. All right, what about bromine? See, bromine's here in row 4. So this means we're going to have to bring in our first row of transition metals. And you remember that your first row is 3D. So what we have row 1, 1s2, row 2, 2s2, 2p6, row 3, 3s2, 3p6, row 4, and now you can tell which order they go in because you see first I have my S block, then I have my D block, then I have my T block. So that means, now let's move this down a little bit. I'm out of room. Okay, so then I have 4s2, 3d. And if you're, again, you need to get down that s orbitals, s subshells have 1 orbital, p subshells have 3 orbitals, d subshells have 5 orbitals. And so if you have 5 orbitals, you have 10 possible electrons. But if you're ever wondering, you can say, well, the D block I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So 10, and then my bromine is going to go 1, 2, 3, 4, 5. 4p5. Okay, what about rubidium? Yep, that is the first element in row 5. So that is an S1. This will have to end in S1. It's S block, and it's the first element. Okay, so 1, S2. Yeah, I'll probably move. Let's see how much room I have. Row 2 is 2S2, 2P6, which gets me all the way over through neon. Row 3, 3S2, 3P6. And you notice that we don't put any Ds in for the first 3 rows because there's no transition metals. There's no D block there. Okay, 3P6 all the way over to argon. 4S2, potassium and calcium, 3D10 to go all the way across the first row of the transition metals. Now we're back over to the P block for P6 to go all the way over to krypton, and then 5S1. Okay, what about lead? Where's lead at? Ooh, lead is here. That's row 6. Uh-oh, look here. That is going to bring in the lanthanide series. Okay, remember for these, row -2, for the lanthanide series, because in this one, you come down here, that'd be row 7. So this is going to be 6 -2 or 4F for that lanthanide series. Okay, so that is going to give us 1S2, 2S2, 2P6, 3S2, 3P6. Row 4, 4S2 transition metals, 3D10, and then 4P6 across the P block. Row 5, 5S2. We hit the second row of transition metals. So we had 3D, now we have 4D, 10, and then 5P6, and now 6S2 for the cesium and the barium. Now, you notice how here I hit the lanthanide series at the very beginning of the transition metals. So that means the next input in order of energy is going to be for F. Then how many electrons is that? Well, F subshells have 7 orbitals based off their M sub L quantum numbers. And so if you have 7 orbitals, that's a possible 14 electrons. But again, if you aren't sure, you can go you could count across. Now here you'll see you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, yeah, you have one more element there, but this is going to be your this goes back to 5D1. We'll talk about this in a little bit. But remember, what you really want to do is remember that for F, for the F subshell, that is L equals 3. So that's going to be M sub L minus 3 minus 2 minus 1, 0, 1, 2, 3, or 7 orbitals, or 14 possible electrons. I think that's the easiest way to do it. But you can also count if you keep certain things in your head. But you're going to get 4F14 going across the lanthanides. Then you go back up to the transition metals because that's next. And you have 4D, now you have 5D, 10, and now we're back into P1 and P2. And again, your P takes, it's the number on the front is the row that you're in. So yeah, that element's a little deep in the table, and you can see that there's a lot of stuff you have to keep in your head. So we will practice this, but a lot of the reason, a lot of the stuff that you would have to know, we would leave for more advanced classes, but we will work with it. There's a good write-up in your textbook on how this works. Let's do an easier one though, tellurium. So right here, okay, that's row 5, and it's in the P block, so it has to end in 5p. 1, 2, 3, 4. Has to end in 5p4. All right. 1s2, row 2, 2s2, 2p6, row 3, 3s2, 3p6, row 4, 4s2. I hit my first row transition metals, 3d10, and then 4p6 going across there, row 5, 5s2. Hit my second row of transition metals. I go from 3d to 4d10, and then I hit my p block again where tellurium's at, and I get 5p4. Yep. Okay. So really, you can, like I've been saying, you can just look at where you are on the periodic table and learn how to do these electron configurations that way. If you get a little confused about the order these should go in, you can go right back up to your Aufbau Principle map and just do that. Because again, we go from 1s, 2s, from 2s to 2p to 3s, from 3s to 3p to 4s, from 4s to 3d to 4p to 5s, and so on and so forth until I got all the way through. So you can use this map as well. Okay, so let's look at these abbreviated configurations. Okay, so the full configuration, as you can see, can get pretty long. I mean, look at lead. Now, we can actually shorten these down to what's called an inner sphere of electrons and an outer sphere of electrons, which is different than core and valence. So don't really get, they're close, but they're different. So your inner sphere, most of the time, a lot of the time, is going to be your core. Uh, with transition metals, you're going to have some d electrons that are in the outer sphere, but they're still core. We'll look at that. But uh, your inner sphere electrons can be written by using the previous noble gas that you passed. So let's say I was working on calcium. Okay, well, to get to calcium, I had to pass argon. So then I just put argon in brackets. And then the only electrons I write are everything outside beyond argon, which is potassium and calcium. Okay, so let's look at aluminum. Let's do that. Okay, so aluminum right here. So that is in row one. Come on. 1, 2, 3. And it's in the P block. It's the first element in the P block, so it has to end in 3p1. Okay, so its full configuration. Did I not do? I thought you could. 50. Oh, okay. So the full configuration, we start with row 1, 1s2. We go to row 2. For lithium and beryllium, that's 2s1 and 2s2. Go to boron all the way across. That takes us through 2p6. 2p6 is once we reach neon. Then sodium and magnesium, that's going to be 3s2, and aluminum is 3p1. Or what we can say is, what's the noble gas that we pass before getting to aluminum? Well, it's neon. So what we can say is I'm going to put neon in brackets. That's my inner sphere of electrons. And then everything past neon is going to be row 3. So it's going to be 3s2, 3p1. So your neon, of course, takes care of those first 10 electrons. So these abbreviated configurations are much easier to write. So let's try strontium, which is right here. So that's for row 5. Okay. So we have to do row 1, row 2, row 3, row 4, which of course we hit the first row of transition metals, which will be 3D. We go all the way across the transition metals, so it's 10 electrons. Then we hit the 4p6. And then for strontium, you get 5s1 at rubidium, 5s2 at strontium. However, all the way through row 4, before we got to strontium, we passed krypton. So your abbreviated configuration for strontium is going to be your inner core of your inner shell of krypton, and then everything outside of that is going to be row 5 or your 5s2. So these configurations are much nicer to write. It's in row 2. It has to end at 2p2 because boron is 2p1, carbon is 2p2. So we're going to say 1s2, 2s2, 2p2. Or, I mean, we passed helium. Inner shell, or inner sphere of electrons. And then everything outside of that is your 2s2, 2p2. What about aluminum? Well, that's a row 3 element, and it's your 3p1. So that's your 1s2, 2s2, 2p6, 3s2, and 3p1. So, of course, neon is the noble gas that you pass before getting to aluminum. That's your inner sphere. And then everything in row 3 is outside of that. So that's your 3s2, 3p1. Now I'm going to give you another big one that I probably would not ask you on an assignment, but again, all the way down there at the very bottom of the periodic table. So again, you see that we have our actinides, which are going to go here to 4F. Oh, sorry, lanthanides, because it starts with lanthanum. And then your actinide, or here, starts with actinium, and that's 5F. So these are both going to come into play. And then you have 3D, 4D, 5D, 6D. So we're going to have to deal with that. And this is all the way down at 3, 4, 5, 6, 7. So this has to end. You have 1, 2, and 7p2. Okay, well, let's do the full configuration, and you'll see why this one really shows you why we enjoy these bridge configurations so much. Okay, so row 1, 1s2, row 2, 2s2, 2p6, row 3, 3s2, 3p6, row 4, 4s2, S block, then D block, 3d10, and then P block, 4p6, row 5, S block, uh, D block, P block, row 6, 6s2. But now remember, we jump down to the lanthanides and we go 4f, 14, because there's 14 possible electrons in the 7 orbitals of an F subshell. Then we jump back up. We go, so row 6 is 5D, and then 6P, then P block, and now we're down to row 7, 7s2. And if we go SFDP, now we need 5F. Again, it's an F subshell, so it's 14 electrons. Then we need the 6D electrons, and then we end in 7p2. Oh boy. Now, I could have you write all that out on an assignment, or we could say, well, we passed radon to get there. So that takes care of the first 6 rows. And now all I need is everything that's in row 7. 7s2, 5f14, 6t10, and 7p2. So much nicer to write. What about one that's not so far down? So SB, antimony, right there. That is in row 5. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. We hit our first transition metals, 3d10, 4p6, 5s2. Hit our second row of transition metals, so 4d10. And then antimony is in 5p, 1, 2, 3. 5p3. Or what do we pass to get there? Krypton? Okay, so that's going to be inner sphere of krypton, outer sphere of row 5, which is going to be 5s2, 4d10, and 5p3. So you will likely see, some questions saying do both the full and abbreviated configurations. So you'll need to know how to do both. Alrighty. Now we need to talk about what's called valence electrons. Valence electrons are the electrons you'll find in the outermost energy shell. So you're going to go through, you're going to do a configuration, and then you're going to find the largest value of n. All of the electrons in that largest value of n are your valence electrons. Those are your important electrons because those are the ones that do chemistry. Those are the ones that will be involved in bonding. If you have an electron taken during a reaction to form an ion, that's where it'll come from. It can come, so this is why I say inner shell, outer shell is not quite the same as valence core, because then everything else that's not a valence electron is your core, or those are your core electrons. Now, I will be straight up and honest with you. Transition metals can be a little weird. Sometimes electrons in the energy shell and the lower energy shell, but in the d subshell can act as valence. Sometimes they don't. And again, that would be something we get into at a more advanced level. For what we're doing here, you're going to look for that highest value of n. Those are your valence electrons. Okay? So let's look at potassium. Potassium's right there. 1, 2, 3, row 4. That has to end on 4s1. And I'm just going to do, well, 1s2, 2s2, 3p6, 3s2, 3p6, 4s1, or, see, what did we pass to get there? Argon? Argon 4s1. Now, sometimes your abbreviated configuration can tell you which ones your valence electrons are. You can always double check with the full configuration, but what we're looking for is your largest value of n is n equals 4. That is bigger than 3 or 2 or 1. So n equals 4 is your largest value of n. So that means you have one valence electron because it's 4s1. If you were asked to, we talked about the box diagrams. If you were asked to draw the valence electron box diagram for potassium, you would draw your box, 4s, and put your one electron in it. Let's look at germanium. Oh, it's in row 4. There it is. Germanium. Now, You see we have to do our 1s2, 2s2, 2p6, 3s2, 3p6. Now we have potassium and 2, but then we have our 3d10 to get to germanium. Now we have 4p2. Our abridged configuration is, of course, or abbreviated configuration is argon 4s2, 4p2. And as you can see, n equals 4 is my highest value of n. And so I have 4 valence electrons. This box diagram is going to look a little different. You're going to include the 3D in the box diagram, even though they're not counted as valence. So we would have 4s, 1, 2, 3, 4, 5, 3d, and 1, 2, 3, 4p. So you get 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 4p. You have to follow Hund's rule, you get that. Now let's do phosphorus. Phosphorus is in row 3, and it's going to end in 3p3. Oops. And you can see that your highest value for n is, your largest value of n is 3. So n equals 3, and that means you have 5 valence electrons. Again, your valence box diagram. 1, 2, 1, 2, 3. So valence are not hard to pick out. You're just looking for that largest value of n. Those are going to be your valence. Okay, we're going to talk about transition metals. This is going to be stuff that you're going to want to know, at least this opening material. I'm not going to really try and make you guess what some of these configurations are, but just know that it gets a little wonky. And so the first thing transition metals will do is called the half fill configuration. So you're going along, you're filling in the D subshell. And so let's say you're in the 3D, the first row of transition metals. You're going along, you go 3D1, 3D2, 3D3, and then you would expect 3D4. No, what happens is you go from 3D3 to 3D5 because the transition metal strips an electron from the 4s level. So you have 4s1, 3d5. And this happens because at that point you've maximized the spin and you've maximized Hund's rule in your degenerate d orbitals, and you're getting all kinds of quantum exchange. Okay? So that's the first thing that happens. Then you're going along. So then after that, you'd get 4s2, 3d5 because it's going to want to maintain that high spin as long as possible. Then you'd start putting electrons, pairing them into the D subshell until you get across to 3D7, 3D8. Once you get it to 3D8, you're going to steal an electron from the 4s again and go to 3D. You're going to skip 3D9 and go to 3D10 because just like the half fill configuration being very stable, a completely filled subshell is very stable. And a partially filled S subshell is more stable than a partially filled D subshell. So just know, like this is going to happen, and every single row of transition metals has its own pattern on how it does this. So I'm not going to make you memorize all that, but you're going to want to make sure you know that this exists, and you're going to want to understand it at least a little bit. Go through what we do on the slides, go through the chapter, make sure you're starting to wrap your mind around what happens in the transition metals. So up here at the top, we have vanadium, chromium, manganese. This is going to illustrate the half fill configuration. Okay, so vanadium. So it's going to be these three metals right here. Okay, So you see vanadium is 1, 2, 3, so 3d3. So I'm just going to use the abbreviated configurations. So vanadium is going to be argon 4s2 3d3. Now, at chromium, you're not going to get 3d4. It wants to maximize that spin, so it's going to steal an electron from 4s. You're going to get 4s1 3d5, which is now those d orbitals, they all have one electron in them. Your spin is maximized, and now you're getting all kinds of quantum exchange energy. Whereas your manganese then is going to immediately refill your S subshell 3d5. So chromium is your half fill atom. That's where it occurs. Now, nickel, copper, zinc is where the other theft of an electron from the 4s level happens. But this is later on down the row. This is not called half fill. Chromium is your only half fill. But down the row, you still get this same kind of theft where it wants to fill up the D subshell, and it happens like this. So nickel is going to be argon 4s2 3d8. Now we're real close because your D subshell can hold a maximum of 10. So it's going to want to get 10 in there. So what copper is going to do, 4s1 3d10. And so then your zinc is going to then refill your S subshell. Because again, at copper, the metal's going to go, if I can just get that D subshell filled, I'm going to be much more stable. So it's going to steal it has an electron come in for 3d9, but then to fill itself, it still steals an electron from the 4s level. Now, I'm not going to make, again, at this level, I'm not going to make you learn all of the transition metals. I would make sure you know how to do at least this first row, know where the half fill is, understand the pattern across the first row, because like I said, every row is going to have a different pattern or a different rule. Okay, so then there's the problem of working with the lanthanides and the actinides. So if we go down, we see lanthanum. Okay, so that's in row 6 right here. And so the first element of that row is going to be your xenon 6s25d1, because your lanthanides and actinides are still transition metals. Most of them are radioactive, like uranium, plutonium, stuff like that. But your first element there is going to be 6s25d1. Then, as you go on cerium, you're going to start filling in the F block. So you're going to get 6s2 4f1 5d1. But then what happens is, oh, what's the name of that one? Anyway, PR. Praseodymium. These names get more and more intense as you go along. Okay, praseodymium. Okay, so what's going to happen then is the electron in the D subshell, the 5D subshell, is going to be stripped and put into the F subshell to start filling in the energy levels there. And so your uh, praseodymium is going to be xenon 6s24f3. From there, you will fill the 4f all the way over to 14 until you get over to Lu, or lutetium. Oh, it's down here. So lutetium. So now you've filled to 4f14. That's where you're going to put back in your 5d1. From there, you would hop back up to the transition metals and go all the way across to your 5d. I had myself confused there for a minute because I have a typo on here. But so then you go from the lutetium back up to your 5D row, your 5D transition metals, and you're going to fill across going towards 5D10. The mistake is this is not PR. That's PET, it's platinum. Until you get down to your iridium. Your iridium, platinum, and gold are going to do something very, very similar to what happened up in your 3D metals. So you have iridium, which is 6s2, 4f14 is filled, and you have 5d7. Now, what happens at platinum, instead of waiting, it's actually going to go ahead and strip an electron from 6s, put it in the 5d. And the reason this happens in different patterns is as you go up in your value of n, these subshells get further and further apart in energy, and electrons are constantly trying to find the lowest energy. And so your platinum is going to strip down to 6s1 and fill into 5d9, and then immediately to 5d10 for gold, at which point mercury would just fill in back to 6s2. But you see, this is a slightly different pattern than what you saw above at 3D, but this is the pattern for row 6. But so again, I'm not going to make you memorize every row. Just work on row 3, get that down, know where your half fill is, know where the nickel, copper, zinc, the theft from the 4s there. Know your 3D. Well, but I just wanted to show you the pattern for another row to show you that this keeps happening as you go through your transition metals. And so your actinides will have similar patterns to the lanthanides. Your actinides start with actinium, and that is your 5F row. Let's see. Let's see. The part of the periodic table known as the main group elements, that's your S block and P block. Those are your main group elements. They maintain their patterns all the way through. So if it's S block, it's S1, S2. If it's P block, it's P1 through 6. And then if you're talking about your if you're talking about valence electrons and it's in an S block or P block, you know how many valence electrons you have by the column that you're in. So if you're in column 1A or column 1, that's your hydrogen column, you have 1 valence. Column 2 is 2 valence. And you go across and you either have 3A through 8A or 13 through 18. That's going to be 3 valence, 4 valence, 5 valence, so on and so forth. So you can actually know the shortcut to your valence electrons if it's a main group element. So let's kind of end with an exercise today. Let's do full and condensed electron configurations for chlorine, strontium, lead, and CF, californium. That's an actinide. CF is right there. So we're going to try to predict what that is. I'm actually going to give you the actual configuration, but on any assignment problem where you have one of those, you'll probably have to, look it up or get a little help. That's fine, just as long as you're practicing and you're getting used to these electron configurations. Now, if you go to AI for chlorine, I will mock you relentlessly. But for your actinides, lanthanides, some of your transition metals, I fully intend that you'll get a little help on those because they all have unique patterns to them. So let's look at chlorine. Okay, so that's right here. It's a 1, 2, 3. It's row 3. It's going to end in 3p, 1, 2, 3, 4, 5. Okay, so row 1, row 2. Now row 3, 3s2, 3p5. There's the full configuration. What about the abridged configuration? Well, we passed neon. Condensed configuration, so neon. Then row 3 is everything outside of neon, so 3s2, 3p5. If you were asked about valence, this has 7 valence electrons because n equals 3 is my largest value, and I have 7 electrons in that value for n. Okay, strontium. Strontium, where's that? Oh, it's down here. So that's 3, 4, row 5. That's going to have to end on 5s2. Row 1, row 2, row 3, row 4. Now I'm going to hit my first row of transition metals, which it's 3D. Go all the way across, that's 10. Back to my main group elements, so 4p6. And then down to row 5, 5s2. Let's see, I passed krypton to get to row 5. So my condensed configuration is krypton, 5s2. So let's do lead. And try to do these before we go through them, see if you're getting it. Lead, where's it at? Uh-oh. That is in row 6, which means I'm going to have to cross the lanthanides. That's 4F. And then, of course, row -1, that's going to be 5D. Okay, so row 1, row 2, row 3, row 4, then 3D10, and then 4P6, row 5, 5s2, let's see, 3D40, 4010, and then 5P6. Now cesium and barium, that's 6s1 and 2. And now I go down to the lanthanides, which is 4f14. Then back up to hafnium, which is right here. So my transition metals, I go from 40 to 5d, 10, and then lead is 6p2. Okay, so what did I pass to get there? Xenon. So xenon's my inner sphere. My outer sphere is all of row 6, so from 6s to the end. Okay, now this one, if you were asked about valence, your highest value for N is 6, and I have 4 valence electrons. I have 1, 2, 3, 4. Okay, so what's the last one? Ooh, californium. Yeah, it's my actinide. Okay, that is going to be a row 7 thing because it's an actinide. That is 5F. What is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5F10. Okay, so let's see. Row 1, row 2, row 3, row 4, row 5, let's see, row 6, 6s2, but then we get the lanthanides, 4f14, and then 5d10 and 6p6, row 7, 7s2, and then I go from francium to radium, that's my 7s1 and 7s2, and then I jump down to the actinides and I count it across to, oopsies, 5f10. Now, which noble gas did I pass to get there? Radon. So that is going to be Rn as my inner sphere. And then row 7 is 7s2, 5f10. And as you notice, if you were asked, 7 is your largest value for N, so you have 2 valence electrons. Okay, so these are electron configurations. We'll finish up tomorrow with this chapter tomorrow with uh, uh, trends across the periodic table. All right, talk to you later.